on then. We're going to go over to Lou now, who's going to continue with his series about exoplanets. So what have you got for this week, Lou?
Right. So first of all, thanks to everyone who has hung in there and endured all the sessions of all the methods that we have been covering to detect exoplanets. It's obviously not so simple, and we're going to add another to that list today. And before I do, Keith, I wanted to say to you, I love the animation of L-Cross that you showed. And I might just point our viewers also to we talk about Eyes on Exoplanets that was developed at JPL. Eyes on the Solar System has all of the planetary missions, and I think some heliophysics missions too, that you can go to. You can see what the spacecraft was doing at the time it was doing it, because it has the spice kernels that replicate the spacecraft orientation and position. So Eyes on the Solar System might also be a nice reference.
And I'll post a link to that in the description for tomorrow when tonight's video is processed. So you'll be able to click it in the description.
If you're using that, the flyby of Pluto on that is brilliant. On Eyes on the Solar System.
New Horizons.
Yeah, it's really good. Yeah.
I'll have to fire that up later and have a look. I don't think I've actually looked at the Pluto one. So thank you for that, Keith. I'll have a look later. Okay, so Lou, exoplanets.
Let's go to exoplanets and see if I can start our slideshow here. Okay, there we are. So we have been through quite a labyrinth in discussing how you find these tiny, tiny objects at trillions of miles of distance that have no light of their own. And so you have to be a little bit creative or have great technology. And we've been through a number of techniques. And today we're going to talk about microlensing. So what is microlensing? How could you use that to detect an extrasolar planet? Well, we are now, thanks to the James Webb Space Telescope, we are now all intensely familiar with gravitational microlensing. And here's the image that we're all familiar with, one of the first 5 images that JWST produced, with the characteristic arcs in here that are the gravitationally lensed and distorted images of very distant galaxies. So we know that massive objects, any mass actually, warps space. And that's from predicted from Albert Einstein's thinking about general relativity. So that's for big objects. I always throw this in. This is the NASA Exoplanet Archive with the latest results from the number of confirmed planets and number of candidate planets. And every time I go there, every week or so, it increases by 2 or 3 or so. So we're making good progress there. So gravitational microlensing. So here we have a situation where we are looking at a very distant star, which is our source star. And in between that star and the observer is a planet, is a star with a planet, all right? And as that star and planet pass in front of the source star, we see a brightening because of this microlensing from the star, from the intervening star, and as that planet moves in front of that light path, we also see a slight brightening, and that is an indication that that planet is there. So this is great. This is great for doing gravitational lensing of very low mass objects, but it's not really very good for trying to do multiple observations, multiple detections of a planetary system, because you only get one shot at this kind of thing. Here's an animation of what that looks like. So Here you see the planet with the star moving in front of a very distant star, and you see the light curve, the brightness increasing. And then as the planet moves in front of that star, that also has a microlensing effect, and you see a slight bump in the light curve, and that is evidence of an exoplanet. Here's some actual data. I forget which star this is. Oh, Ogle 2005 BLG 390. Okay, remember that. Remember that. And so here you see the same kind of qualitative curve. It rises as the exoplanet star moves in front of the distant star, because you have microlensing that's brightening the image. And as the star moves away and the brightness starts to wane, you see a slight bump on the right-hand side there, and that is a exoplanet. Well, as I mentioned, this is great for some things, but not so great if you want to do follow-on observations, and you have to have just the right alignment of the exoplanetary system in front of the distant star. So here we see the number, cumulative graphic of the number of exoplanets detected. And in purple, this third item down here is microlensing. And you can see the little purple streak on top of each of these curves. So not many exoplanets have been detected so far from this kind of technique. And in fact, the very first exoplanet detected with a microlensing technique was in 2003, which was Ogle 2003 BLG 235 MOA, just a catalog number, but in 2003, so fairly recently. And here they are. Here are all of the exoplanets that have been detected by microlensing. There are only 37 of them out of the more than 5,000 planets that have been detected. But this is a really great technique for detecting low mass planets, right? So that are far away from their star, right? So you have separation between the light curve of the star and the light curve of the planet. That's very different than what we had been talking about before, where you want very massive planets for, say, a transit detection very close to the star. So this fills in a gap of exoplanet detection. This is kind of a cool little, as my last slide, this is a cool little animation of the exoplanets that have been discovered over time. And of course, the time is very, very much sped up here using the microlensing. Here, let me play that one more time. Using the microlensing technique. So just kind of where they are and in the sky, and kind of a sped up chronology of detection of exoplanets using microlensing. And brilliant. I will stop there.
Thank you very much, Lou. That's fascinating. Yeah. But as you say, the alignment there is crucial, isn't it? It's you know, if you want to see another event from the same planet, you've got to wait till it passes another star. And obviously, as you said, that's not going to happen very often.
Right. So you would use it as an initial detection, and then say, I think I found something, and then you'd go rely on some other detection methods that could maybe confirm these candidate planets.
Great. Well, Lou, I have to say your series on exoplanet detection has been absolutely fascinating. Thank you so much for doing that.